So this is the first problem of today's div 2. And in this problem, we're given that we have a hand of n cards where each card has a number written on it and a fixed integer k. So now we can perform the following operations any number of times. That is, choose any k cards from our hand that should have all the same number and exchange these cards with any k minus 1 cards, each having any number. So this problem so in this problem, like we are given that we have initially n cards, right? And each card has a number written on it. So like 1, 1, 3, 2, 2. And we are also given k. So let's say k is 3. So in this case, we need to choose three cards that have the same number. And then what we can do, we can, instead of these three cards, we can exchange them with any two cards having any number x, y. And then let's say I had this one, like I had these cards. So let's say I chose these three ones. So I won't have these. And finally, I'll have 3, 2, 2, 4, x and y. X, y can be anything. So finally, we need to find the minimum number of cards that we can have once we are done with all the operations. So now tell me one thing. If let's say I have some cards, I have some ones, some twos, some threes, and some fives, let's say. And let's say 3 occurs maximum number of times. This is occurring maximum number of times. But let's say this is this count. Let's say this is the count. Count is how many times this maximum element occurs, maximum number of times element occurs, its count, and this count is less than k. So now tell me, can you do any operation? Can you do any operation? Yes, no?
No.
No.
No, sir.
Okay, perfect. So in that case, the answer is simply n. Perfect. So now let's say there is, again, I have some elements and there is one element, one number for which the count is, let's say, more than or equals to k. So I can at least do this operation once, right? There is, forget about other numbers. Other numbers are some random 1, 2, 3, 7. There was a x which occurs at least k times, k or more time. So I can do this operation once. Precisely, I'll do this until count is more than k. Once count becomes equals to k, what I can do, I'll again do the operation. Instead of k, I'll get k minus 1. And those k minus 1 cards, first I'll make them equals to 1. Like I'll have all the cards as 1. Then I'll remove, like again, I'll have k minus 1 once card I'll get from this operation. And I have a 1 here. So I'll again have k cards. I'll again do the same operation. But the next time I'll remove this one, like all of these ones are gone. And I'll get k minus 1. I'll say that I want 2s. So now I'll do the same operation with this, then with this. So irrespective of other cards, I'll keep on doing this. Eventually, once I do the operation with this, I'll have k minus 1 cards left. Is it making sense? And then I'll stop. So in this case, my final answer is k minus 1. Is it making sense? Is it clear to everyone? Yes, no? Okay. So let me show you the implementation. This is the implementation. In this, I have first taken n and k as input. Then this is my map for counting how many times each element occurs. I'm counting how many times x is appearing, and this is my maximum number of times the element occurs. If maximum is more than or equals to k, I'll print k minus 1, and this is my solve function. Otherwise, I can print n. Is it making sense? Okay. So let's go to the next problem. So this is the next problem. How many people were able to solve this? Okay, this is also a very like naive problem. If you're able to guess how can you come up with the answer, then you'll be able to solve this. Okay.
Understood, but time ended at that time, so I couldn't implement it.
Okay. Okay. Like first, let's go through the problem once. So the problem is there is a n cross m grid of white and black squares. In one operation, we can select any two squares of the same color and color all the squares in that like in the subrectangle between these two as that color only. So let's say this and this other two squares that we select, they have the same color, both are white. So in between this, all the squares will be colored as white. So we need to find after these operations, such kinds of operations, if we perform these operations any number of times, is it possible for us to have the grid cells, all grid cells should have the same color? So eventually you need every cell of this grid to have the same color. Now, like let's discuss, instead of me telling you the solution, how would you solve this? Like, first of all, what if you had the same color here and here? Then you are good to go, right? So this is the first thing that comes to our mind. If these cells are of the either this or of the same color, or this are of the same color, then we are good to go. But let's say this is not, then what will you do? What is the next thing that you can do? You'll try to break this, like you'll
Should I answer or
yes,
you
yes,
are?
yes. No, I'm waiting for you. Like you can answer. Of course, you can unmute yourself and answer. What will you do?
Yes, I just came up with like a very simple implementation that see there are four corners and I'll
Yes.
be pairing like any two anytime. And the only thing I just want to search is that if both of them are of same color, I want that exact color in the just opposite side. Like if I'll be taking like if you can number them one, two, three, four, and I take from the first row the no the corners one, two, three, four
Okay,
in
okay.
that way.
So 1, 2, 3, and 4.
Yes. So let's say I'm just taking two and three and both are of white color.
Okay.
So what I want is I'll just search for one white color in the first column. If I get it, then I'll surely be able to like color a whole of the board white. And like this works for every like the
Or like
pair of corners.
yes,
Addition.
you can take these two and you can check here, right? Whether there is a
Like that.
yes. The same thing I have also done. Like maybe many would like maybe some students didn't get this, but the approach is this only. See, we'll try to break. So let's say this is the grid. And by the way, thank you. Like whoever told us, like this is the perfect solution. So we have this, and you need to break this. Like first color this much, then maybe take this much, then maybe you would be able to take this much, So like just break your squares, and eventually you can take maybe these two. So what we are like, we first took this and maybe this. Then what I did, I took, let's say, this and this, or maybe something better. Let's say I took this and this, and then I took this and this. So you see what I'm doing. First, this one, like this is in my first column and first row. I have a same color cell in first column, first row. Then I did like this. So this is my last row and last column, right? So I have a cell in last row and last column, same thing in first row, last column, and in last row. So as long as, like, you can see for this any kind of solution, like for any solution, like there may be different ways to implement this, but eventually what we are checking that we should, like, if we are checking for white, there should be a white cell in first row, last row, first column, last column. If white, if let's say white is not present in all of these 4 rows and columns, then answer is no. Same thing for black. If black is present in first row, last row, first column, last column, then you're good to go. Let me prove this. If this thing satisfies, we can always color. Like, let's take a random grid. And forget about other colors. I'll take the white color. So let's say this is white color here, white color is here, white color is here, and white color is here. So this is as random as I can get, right? And one more thing, like, you might think for this column, for this grid, the answer is of course yes, because we have this as black and this is black. But let's forget about this. I said that the grid I should be able to color this in white because I have, the condition is met that in first row, first column, last column, there is a white cell. So how can I do this? See, first operation can be something like, you choose this thing and this thing. So this is your grid that you'll color. This is gone. Like, this is all is white. Then in next, maybe we can pick something like this thing. This thing. So this is also white now. In next, let's say we can pick this one and this one. So this and this. So this complete thing is gone. This is also white. And lastly, we can pick this and this. So this is also white. So you see, like, there is a way you can follow other way also, but it's always possible to color the complete grid into 4, like into a color, if I have first row, last row, and same thing, first, this is last, first column and last column. Is it clear to everyone? And this is the same solution, like what this other student told earlier, that we are checking that if there is at least, like, there are two, like, we are able to find 2 corners with same color, and on any opposite side there is at least one. Like, he's also checking the same thing, like how that would matter. Like, you can take this thing and you can take this thing, so same thing, but this is more generalized way. If every column, if first row, first column, second column, and last column have the same, like they have at least one color which is common, then we can do. Is it clear? Yes, no? Clear to everyone?
Yes. Sure.
Okay. So let's move to the implementation. Like I'll recap while I'm explaining the implementation. Okay. So this is the implementation. In this, I have taken n and m as input. Then I have taken string s. Like this is my grid. So I'm taking the grid as input. Then this is my flag. That if f is 1, then I have found the answer. And if my flag is 0, then I'm not able to find the answer. So I have two characters. Like this is the way we can iterate over. Like I don't have to write this condition, like this code twice. So I'm iterating over my colors. I have black and white. I'm checking for black. What is the maximum row in which this is present? What is the maximum column in which this is present? Minimum row in which this is present? Minimum column in which this is present? Just iterate over the grid and do this thing. If s of ij is equals to the color is x, then find this maximum and minimums. Eventually, if minimum row, minimum column and is 0, maximum column is, this would be -1, not like this. I think when I pasted here, so this is -1 and this is also -1. So maximum column is m-1, minimum row is 0 and maximum row is n-1. Then the answer is yes, otherwise the answer is no. When I'm saying that answer is yes, I need to make f as 1 and break the loop here. Is it clear? Yes, no? So is anyone having any doubt in this? Like who wanted me to recap? Is it clear now? Okay, so should I move to the next problem? Okay, let's go to the next problem. So in this problem, we're given that Elise and Bob are playing a game on n piles of stones. On each player's turn, they select a positive integer k that is at most the size of the smallest non-empty pile. We need to remember this, that they select at most, like maximum number of stones that they can select is the size of the smallest non-empty, not like we cannot choose 0. So they select smallest non-empty pile, and like maximum can be smallest non-empty pile, and remove k stones from each of the non-empty piles at once. So the first player who is unable to make a move because all piles are empty loses. Now, given that Alice goes first, who will win the game if both players play optimally? So first of all, let me explain this problem once. And again, like we'll discuss, instead of me telling you the solution directly, we'll discuss. So what, like first of all, let's say this is the pile, this is another pile, and this is one more pile. So what they are doing, let's say it's Ali's turn. So minimum number of stones in a pile is 2. So Alice can either choose 1 or 2 in her turn. Let's say she choose 1. So 1 stone from every pile will be removed. If she had chosen 2, then 2 stones from every pile will be removed, and then Bob will follow. Is it making sense? Now,
Yes, sir.
just tell me who will win for this 1, 3. Just tell me, like you don't have to tell me the approach, but first tell me who will win. Bob. Okay.
Bob.
How? Like, how will Bob win?
Like first, Alice will pick up one and he will remove one stone from each pile. Then only two stones are left, which is the minimum. Then Bob will
Yeah.
simply remove those
Remove.
two.
Yes, remove all, right? So now who will win for 135? Think for this and tell me.
I think we can actually, what we can do is And there will be say 2 stones left in pile 3. So Bob can actually just choose one and force Alice to pick one, resulting in like some stones remaining in last pile.
Like okay, so can you repeat yourself? First,
Yes, yes,
allies will remove one. Okay,
exactly. So
so 2 and
2
4.
and 4. Now there is like Bob's turn, so he can remove exactly one stone from like both the piles, right? One stone,
1 stone. So 1
1 and 3.
and 3.
Yes. Now Alice has to remove one.
Exactly. So like I was waiting for other people. Like I wanted other people to say allies. This is the perfect like this is what I wanted. Like if you basically like this intuition comes once like you have solved enough problems in game theory. Like otherwise the generic intuition that you might get is for 135, like 1 3 is easy. 135 you might get that allies will remove one, then it will be 2 4, and Bob will remove two or maybe one. So in that case, allies will win, but that's not optimal for Bob. What is optimal for Bob is after we have 2 and 4 stones left, Bob should remove exactly this -1 stones always. Like Bob should give to allies exactly if there are, let's say, more than one piles. So in the first pile, Bob should give exactly 1 stone. Why? Because then allies can only remove this 1 stone and nothing else. And once Bob sees that, okay, either there is only 1 stone left in every pile or there is only one pile left with some, let's say, 10 stones or any X amount of stones, then Bob can just remove all of these or all of these at once. But as long as there is something like 4, 10, 20, Bob should always make this 1. So Bob will make this 1 -3 7 -3 17. Bob should always give allies this because once Bob gives this to allies, allies can do nothing but just remove 1 stone. This 1 stone, right? Allies can do nothing. So this is what, and this is not generic to Bob. This is exactly what allies will also do. Like for winning, they'll try to restrict the opponent's move. Like opponent can do nothing but just remove this one. Is it making sense? There is a DP, like many people wrote DP solution for this, but this is a classical game theory problem. If you know this much, this is problem is done. How many people have doubt in this? Whatever I told till now. Forget about game theory, forget about the implementation solution. But just this thing that this will ensure that you'll win. Like if you are playing, if you always give me the first pile is having just 1 stone and I'm always getting this much, I'll always do nothing but just remove that 1 stone from every pile. So as long as you're ensuring this, you'll always win. Now, how to implement this? See, the implementation is much more simple. Just sort the piles according to the stones. Initially, Elisa's turn is there. So just check if the first pile is having more than 1 stone. If it is having more than 1 stone, Elise wins then and there. Why? Because then Elise will always give Bob 1 stone. Otherwise, if let's say the first pile has 1 stone, so you can do nothing. Elise will remove 1 stone. Now it's Bob's turn. So you have removed 1 stone. So 1 stone has been removed. Let's maintain a variable sub. Like how many stones we need to subtract. So we have already removed 1 stone. Then check what is the number of stones left here. So x minus 1. If this is 0, so this means this is already removed by Li. So go ahead. This is not Bob's turn. Like Bob doesn't take turn here. So we come here, like we had 1 stone here and 1 stone here. So this is 0. If it's 0, so this pile is already removed by Li's. But let's say we come here and we encounter that there's a 2 here. So it's Bob's turn. There are 2 stones here. We already have subtracted 1. So there is 1 stone left. So again, Bob has 1 stone left. Again, Bob has to remove this 1 stone only. So go to the next place. Then we encounter, like we have subtracted till now plus 1. We have subtracted 2 stones up till now. Then next place has 4 stones. So now it's Elias's turn, and 4 minus 2. 2 stones are left in this pile. Since the number of stones is more than 1, Elias will make sure after this point, Bob always gets 1 stone. So Elias will just remove 1 stone and Bob will get 1 stone. Now Bob cannot do anything after this point. He'll just on keep removing 1 stone. And Elias, if Elias encounters that there is some X, Y, Z kind of pattern, that is, there is 2, 4, 10 kind of pattern, Elias will remove 1 stone. And if Elias notices that it has X, 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 like something like 3, 3, 3 stones, then Elias will remove all at once. Or if Elias notices that there is just one pile left, which has 10 stones maybe, then Elias will remove all at once. But Bob will always get 1 stone in the like pile which is having minimum number of stone. Is it making sense? So this is what we like. Implementation is this thing only, very simple. Just maintain this things. Sub. How many stones have been subtracted? Is it clear? And by the way, whoever like told this, like this thing. So this is the key to this solution. Like you can solve this problem using DP, using like many other ways, but I think the intended solution would be this only, like use game theory. So let me show you the implementation. So this is the implementation. First, I have taken all the number of piles. Like I don't have the DP solution. Like you can just, okay, if you want from me, particularly me, so I'll have to write it down, and then maybe after the like contest, just like after the session, just tag me in a query. Like I'll give the solution there and we can discuss that also. But I don't have it with me right now. Like why I said people had solved it using DP, because after the contest I went through the submissions and I saw that there. So in this we have taken n as input, then we have taken array A, like the number of piles in the input, like number of stones in each of the piles. Then we are sorting the piles according to the number of stones. This is the subtract and this is winner. If winner is 1, then Elias wins, otherwise Bob wins. Bob winner is initially 0. This means like whose ever turn is done is the winner, like because maybe the next guy didn't like was not able to make the move. So currently it's 0. It means now Elias's turn is there, and if Elias is not able to make the turn, then Bob will win. So that's why winner 0 means Bob, winner 1 means Elias. So we are iterating through the piles, then these stones in the piles. So first, whatever is subtracted till now is subtracted from AI. Whatever stones have been removed will be removed from the ith pile, that is the current pile also. If AI is 1, this means there is no other move than this, like just remove this 1 stone. So just remove the 1 stone, and now earlier it was Elias's turn, now it's Bob's turn. So we are like this. I have explained this in, I think, in the last PCD also. This is nothing but if we have zeros and ones, instead of writing if else, that if it's 1 make it 0, if it's 0 make it 1, we can take XOR, and we are adding this to subtract, like we are removing this also. So add this here. Then if AI is more than 0, so this means AI is not 1 and it's more than 0. So basically this means AI is more than 1, right? So if AI is more than 1, this means that the current player has an option to give the next player or its opponent exactly 1 stone in the minimum pile. So at this point, the winner is decided and we break the loop. If winner is 1, then Elias, otherwise Bob. Is it clear? Like why we break the loop? Why we are breaking the loop? Because the winner is decided here. That's why. Like game theory problem, like game theory is a completely different I would say problems, like problem set. If for that you'll have to, like, there are many concepts. Like game theory is itself, it's completely different. Like you'll have to learn nim game, variations of nim game, and there are some other things. So, like, quite frankly saying, if you haven't solved game theory problems like earlier, and somebody randomly throws a game theory problem at you, it's very unlikely that you would be able to, like, you might be able to solve it intuitively, or maybe some using some other ways, or maybe it's completely something different than what is intended. But solving using classical game theory is very difficult unless you know the basics and you have solved the problems on this. Like otherwise, like coming, like reasoning this only, that if you have, like, if the opponent is given only one stone minimum, like minimum pile is having just one stone, then the opponent will always lose. So coming up with this, I would say, theorem, or like for coming up with this approach, or coming to this conclusion is very difficult. Like you would, like, probably you won't even think in this direction. So this is one thing. Is it making sense? So, and how, like, game theory problem, like you can find game theory problems everywhere. Like again, I think game theory tag is there. It's games, not game theory. On Codeforces, it's games. Okay, XOR is basically, see, if you have zeros and ones, see, binary zeros and ones, and in decimal 0 and 1 they mean the same thing. Like 0 in binary is same as 0 in decimal, 1 in binary is same as 1 in decimal. So let's look in binary. If we have 0 XOR 1, what will you get? You'll get 1. And if you do 1 XOR 1, you'll get 0. So if winner is 1 and you're XORing with 1, you'll get opposite 0. And if winner is 0 and you XOR with 1, you'll get 1. That is again opposite. So whatever winner is, if you XOR it with 1, you'll get the opposite. So that's why. Is it clear? Yes, game theory doesn't have many problems. Like game theory is not that versatile. Like I'm saying, you should just, like, have an idea. If you have solved, like, let's say, some good number of problems, then game theory problems are simply this only. Like how would you, like, what's the most optimal way for one to play out? Okay, let's continue further. No, but it's not binary. I'm not saying array. Okay, let me explain. Like this guy is having doubt. Like I explained this in the last PC, maybe you're not present. See, if you have 0, this is binary representation. In binary, let's say I have a 0, like let's say this is a bit, which is 0. If you take XOR of this with 1, you'll get 1. And if this was 1, just look at these values and these. If you XOR this with 1, you'll get 0. So for 0, you're getting 1, and for 1, you're getting 0. So you're getting opposite of what you had if you XOR with 1. So if winner was 0, if winner is 0, then if you XOR with 1, you'll get 1. If winner was 1, if you and you XOR with 1, you'll get 0. So basically this is same as if winner, so if winner is equals to 1, then make winner as 0, else set it as 1. So this is exactly what I have, what is done by XOR. Is it clear? Yes, from 0 to 1 and 1 to 0, just getting opposite. So someone had doubt, like, why we are using the break, because we already have the winner at this point. There is no point in going like again through the loop. Is it clear? Any doubts? I'll share the code after the session. Like I have already explained like how we decide, because once I have explained here, right? 135. I dry run this. Like you can like see how I have dry run here. Like 135. Once anybody gets something which is more than one, they'll ensure that the opponent always gets one. That's it. So let's go to the next problem. Like if you are still like, how many people have doubt in this? If many, I'll discuss it again. But if only like one or two have, we can discuss it after the PCD ends. How many have the doubt in previous problem? Okay, if you don't have doubt, like write it's clear. Otherwise, say like write you have a doubt. Okay, I'm only getting clears in the chat. So I'll go to the next problem and we can discuss it afterwards. So in the next, we are given that we are given two integers n and k, given a sequence A of non-negative integers of size at most 25, such that the following condition holds. Like we're given n and k, and we need to find a sequence A of non-negative integers such that the size of this is at most 25, and there is no sequence, there is no subsequence of A with sum equals to k, and for every v between 1 and n, where v is not equals to k, there is a subsequence of A with some v. So n and k can be between 10 to the power 6, 2 and 10 to the power 6, and k is between 1 and n. So let me explain this. And here there is one more thing that I have to, like what we need to print. We need to print first the size of the sequence that we have found, m, let's say m would be between 1 and 25, and then we need to print the elements or the numbers in the sequence. So let me explain this. So we are given n and k. Then we need to print a sequence, find a sequence whose, let's say this is the sequence, and any subsequence should not have sum as k. Subsequence is basically, subsequence doesn't mean continuous. Okay. Subarray means continuous. Subsequence doesn't mean it has to be continuous. So any subsequence shouldn't have sum as k. Now, for any value between 1 and n other than k, there should be a subsequence which has sum as this value. So this is given to us by that statement for all v between 1 and n, like where v is not equals to k, there is a subsequence of a with sum equals to v. So this is okay. Now, first of all, is the problem statement clear to everyone? Like what we have to do? Or anyone is having any doubt on the problem statement itself, like they are not able to understand the problem? Okay, like let's brainwash a little. Like you can just tell me like how do you think this problem can be solved? Like this problem is simple. Like I won't say simple, like, but it's once you get the intuition, the implementation is simple. So just think for 2 minutes. Powers of twos. Okay, nice. Something else. Like let's say, what, like first of all, tell me, should you get like your like any subsequence, or forget about any subsequence, your complete array should like, what is the maximum sum that you're looking for? Maximum sum, any subsequence n. Okay, so maximum sum that can any subsequence can have is n. So in that you're basically taking all the elements. Why? Because the elements are more than or equals to 0, they are non-negative. So your sum of complete sequence is n, right? Is this much making sense? Okay. Is my voice lagging, or is it like clear to everyone? Like for how many people? Okay, I think if it's like lagging for just one, I think like probably the internet issue is on your side. So like I was saying, powers of 2 is okay. But now how to make a sequence from this? Powers of 2 is perfectly fine. How to incorporate that k? Why powers of 2? Basically, you need to think this also. Okay, let me see. The problem is very simple. It's just like, how would you implement this? See, we start, we'll like, let's have 1, then 2, then we can have maybe 4. Like this way, let's try to include elements, powers of 2s. So first, let's say sum is 1. So, and by the way, if someone asks you what is the sum up till now, you can just say it's 7, and the next element that you'll add is 8. So first you add 1, then you add 2. So the next element is always whatever the sum is up till now. The new element that you're trying to add, new element that you're adding, is equals to sum plus 1, whatever the sum is up till now. Now tell me one thing. If you decide to add this new element here, you'll get every sum. You'll get every, like there's a subsequence using which you'll get every sum between. Can someone tell me what should I write? New sum between, like using this 8, you can get every sum between 8 and 15. How? Let me show you how. 8 is just this. You can get 9 using 8 and 1. You can get 10 using 8 and 2. You can get 11 using 8, 2 and 1. You can get 12 using 8 and 4, like this. You can get every sum between 8 and 15. So you can get every sum between a new element. Whatever new element was, new element is sum plus 1. And new element is that the element that you're trying to add to your sequence plus sum. So you'll get every sum between these two, inclusive. So if k is between these two, then you cannot add this thing. Then you cannot add this new element. Otherwise you can add. Otherwise you can add this element. So first of all, is this thing making sense? When we can add and when we cannot add this, like otherwise we can continue to powers of 2. Like we'll come to this point in a moment. What should we add? In case we are not able to add, what should we add? But is this first of all clear? When to add and when to not add? These are just powers of 2 that we are adding in the sequence. Now, if you are able to add, perfect, just add and continue. Update your sum, continue. If you're not able to add, what should we add? We should add something for which we should add something here. Let's say it is x, such that x plus sum is less than k. Is it making sense? X plus sum, basically x plus sum should be less than k. And all the others would be also less than k only then. Right? Is this thing making sense? We should add something x for which x plus sum of previous elements is not more than k. Because if it exceeds k, I have already explained that you can get everything between x, and if x is the new element that you're adding, x and x plus sum. So your this thing should be less than k. If this thing is more than or equals to k, you can get everything between x and x plus sum. So x that needs to be added should be less than k minus sum, or more specifically, kx should be k minus sum minus 1. So this is the number that you need to add in case your k turns out to be between minimum element, that is new element, not minimum, but new element, new and new plus sum. So if this turns out to be true, you need to add this. Otherwise, just keep adding powers of 2. 1, 2, 4, 8. Once you get that your sum is finally not like less than n, that is you're either equals to n or more than n, then what will you do? Anyone? Like what should we do? Like there is one more thing that is left. Can anyone tell me? We should get every sum between 1 and n inclusive, right? We need to make sure that this is also true. Like earlier, why did we stop at n? Because we don't have to go beyond n. Like the maximum sum that you need in subsequence is n. So that's why, and maximum sum in subsequence needs to be n. So we basically did that our sequence sum is at max n. We stopped there. But now we already know that k is not, like we cannot get a subsequence of some k, but this thing needs to be made sure. How to do this? Like this is really easy. Like not add 1. If you keep adding 1, you might get k also. Basically, one thing is clear, that up till k, you have everything. Less than k, you can get every sum because of this. Less than k, you can get everything. How to get between k plus 1 and n? How to do this? Only you have to come up with this thing. No, if let's say vi is more than k, then what will you do? If let's say your current element is more than k, then what will you do? Add k plus 1 and powers of 2. Like how? K plus 1 and k plus 1 plus sum and so on. Like why k plus 1? If vi is more than k, like let's say you find it, like you already have a sequence, and you find over iterating over those, you find that there is an element which is more than k. So what will you do? If there is an element more than k, what does that mean? That means that after this point, after you did for k, that you kept adding powers of 2's, and there was an element which itself is more than k, right? This element is more than k. So you found this element. So what should you do? Basically, if k is not there, This means if k would have been there, see, what sums am I missing? I need everything between 1 and n. So what sums am I missing? I'm missing this thing plus k, because k is not there, right? K sum I cannot get. So you cannot get this element. This is what you added, right? But after k. So you cannot get element plus k. Why? K is not an element, but k is sum. This is sum. You cannot get element plus k because k is not there, simply. Right? Now tell me, what should you add? You should add element plus k. If there is an element, like I don't know, like maybe you got confused. See, let me recap. There is this sequence that we made. We ensured, like up till now, what we ensured, that no subsequence sequence of some k exists. This is clear to till now, right? How we did this? We added 1, 2, 4, 8, 16, and then after a point we just saw that, okay, if we add 32 here, then 32 plus sum, this is the sum, 32 plus sum, and just this 32, this is k is between these, so we cannot do this. So we decided that we are going to add x, and x is nothing but k minus the sum, which is 31 minus 1. We'll add this since, so that we don't get k. And then we continued further till we got the complete sum as n. Maybe it's like sum is not less than n, like the sum of this sequence is more than or equals to n. Then what did we do? We go iterated through these elements, and for the elements which are more than k, you cannot get some element plus k. Why? Because k is not there. So if k is not there, you cannot get element plus k. So just add element plus k in your sequence. That's it. Is it clear now? Yes, you just add element plus k. Why? Because element plus k is not possible. Why element plus k is not possible? Because k is not present in the k, like k is some subsequence is not present. So you cannot get element plus k. If you cannot get element plus k, just add element plus k to the sequence. And why does this always work? Because how many elements will you add at max? 12. Why? Like, because again, we like, you can look at the problem constraint. We added 1, 2, 4, 8. There would be around let's say 12, 13 elements like this. And after that, because after that point we'll reach the n, and you can check for k, and for each element, if it is more than k, we are adding element plus k. So our elements will at max double, so less than 25. This is easy, like this is easy problem. Like if we, like, I don't know, maybe like this seems to be complicated, but it's really simple. Like what we are doing, we just make 1, 2, 4, 8. Then we decide that, okay, this element cannot be 16. So we decided what needs to come here. Then we continued. After a point, we reached a point that the sum is now more than equals to n. So we iterated through our elements. We see that, okay, this element is more than k. If this element is more than k, let's call this as element. So this, now we cannot get a sum of element plus k. Why we cannot get element plus k? Because quite frankly, n k sum is not present. K sum in this is not achievable using any subsequence, because we have made sure. So we need to add element plus k to this sequence. That's it. And we are done. And all other sums are possible. I can prove, like I have proved, you can see that everything other than element plus k is possible. Only element plus k is not possible, because k is not present. So let me show you the implementation. So we have taken n and k as input. This is the sum up till now, and this is not needed. So while sum is less than n, my new element will be sum plus 1, like whatever the sum was up till now. This is same thing, 2 power. If new element is equals to k, you cannot have this as k. So this is a corner case. Don't take k as the new element. Otherwise, Otherwise, like, this would be handled here also, by the way. But just do this thing that mn is minimum is this thing, maximum is this thing. You will get everything between these 2 points, minimum and maximum. If k is between these two, like I said, this you get from the inequality, that you need to use this element. Otherwise, just use new element. Add whatever you like, whatever element you used is in the last position of the sequence, add it to the sum and continue. Once we get out of this loop, this means that sum is now more than n. So just check that while iterating through this, if is more than k, it means that we need to insert vi plus k. Why vi plus k? Because k is not present, so vi plus k is also not present. Finally, we can print the sequence. Like 2010 would be like, it would take me 10 minutes to write those things down. And plus it is like, there's a chance that I might write, like, since the calculation will be long, it would take me it's quite possible that I'll write something wrong. But by the way, is the idea clear? And don't look at the like input output data in the problem. Why? Because they are given like that, like 1 1 1 1 1. Like this, basically there is many ways that you can form an answer for a set value of n and k, but this way you'll be able to find answer for every n and k. So okay, yes, okay. Yeah, so that's it, and thanks for joining. Bye bye.